Okay, folks, so we're looking at assignment one, and we're going to try and see how we can start tackling this. And I mean, I don't want to spend too much time on looking at problems like problem 1A and B, but it's important that we recognize that we can pretty quickly see that 1A and 1B are geometric series because we see what's happening between terms. We see the common ratio each time is being multiplied by a common ratio. For 1A, you see that it's being multiplied by 1/3. And for 1b, we see that it's being multiplied by -1/2. So for instance, for a problem like 1b, we can say, well, we know that the first term is 1. So we called that, when we did this before, we called that a. That was what we did before when we were using the series in previous courses. And r was -1/2. And we knew that the infinite sum, if this r actually is less than 1, then we know that indeed this series is going to exist and that the sum is going to converge to some number. And we learned that the formula was going to be simply a formula that looked like this, a over 1 minus r. So when we plug it in, it's a 1. This pen is not working as well as I'd like, but that happens. We'll figure it out as we go. And that should get us a nice sum of 2/3. So that's when it's given to us clear as day. Hopefully we'll be able to figure those out. Other problems, they're not so clear, right? You have something like this, and you say, well, I have this series, and it is absolutely not something that looks like it's being, whoa, how'd that happen? Let's bring that back. It's absolutely not something that's being multiplied by the same amount every time. And this is going to go all the way up into infinity. And what we have to recognize is that we have our laws of logarithms, and they are still our friend. And we can now say that's going to be ln of 1 minus the ln of 2 plus the ln of 2 minus the ln of 3 plus the ln of 3 minus the ln of 4 plus. This is going to go all the way up until we have some last kind of minus the ln of n plus 1. And as this is going to infinity, as this goes to infinity, this is basically going to be approaching negative infinity. And that's why 1c diverges, because although these are canceling out here, and these are canceling out, and this ln of 4 here, that's going to cancel out with the next ln of 4. Remember the ln of 1 is 0, right? So we have a 0 here. So we have 0 minus everything that's been canceling out. Everything's getting canceled up until you're left with negative infinity. And that's why this indeed diverges. Okay, so we're going to skip on to a problem like 3b. Because 3a, hopefully you recognize. If you have to write out a few, but hopefully you'll learn what I'm about to say about 3b. Hopefully you'll be able to use on 3a and a problem like 3c as well. So if we start thinking about this, right, we have this series that is going from 0 to infinity of this series. And it's important that we kind of figure out what's going on here. Now, for some people, they can go directly into simplifying algebraically, but for others, it's far easier to start writing out series. So you can kind of start writing it out if you like by plugging in 0. So if you plug in 0 for the first term, you're going to have -1 to the first times 3 over 2 to the 0, right? That's because we plugged in 0 for n. So we got 0 plus 1, and then we had 0 in the denominator, and that's going to be equaling -1 times 3 over 1. The next term, well, if the next term we go in and we plug in 1 into this, we're going to get -1 squared times 3 over 2 to the first. -1 squared just becomes 1, so we get 3/2. We could keep doing this, and we are going to see a pattern emerge. And I'll do it one last time. And there's going to be a pattern here. And the thing that we have to recognize is that there's a common ratio every time, and the common ratio looks like it's being multiplied by -1/2. So the first term this is that a term is -3 and r equals negative. So it's just like what we did before. Notice the -1/2 here is less than, the absolute value of r is less than 1, so we do have a convergence. And now we can say the sum is going to be a over 1 minus r, which is indeed -3 over 1 plus 1/2, which is -3 over 3/2. And I think that's going to be a nice, pretty -2. Now, some of us can look at this and say, wow, that was easy, right? We saw that when you write it all out, but we might want to just see, could we do that earlier here, right? Could we do that earlier by looking at the initial? So I'm going to change colors here. And we could rewrite this a little bit. Watch what I'm going to do. And by doing that, I basically said, this area right over here, I actually want to be just some exponential function to 1 power of n. And I have a whole lot of stuff in the front here. So then I can rewrite it. And for some of us, that's easy because this is what we saw when we did sequences in the past, right? This is what we used. We said, hey, it's kind of there's some kind of initial term here, a times r to the n. That's kind of what we used last year when we did sequences and series for geometric series. So we can recognize this, and then we can then use this formula over here. So this is one way to do it. Notice that the a is here and the r is there. And this will work when we're using n equals 0 as our starting point. So that's just one thing that we could use. Now, when we're looking at these problems, remember there's other things that we can start doing. We can start thinking about, does r converge or not? But this idea of r being less than or equal to 1, so therefore if r is greater than 1, we know it's not going to converge. If r is going to be, -18, for instance, it's not going to converge. The series is going to diverge. So we can check that convergence right away by seeing, if we look at this thing right here, if this expression, this r, is less than 1, we know converge. So when you look at a problem like 1c, that might be clear as day, because you might say, oh, it's pretty quickly to see what the r is going to be. 1e, hopefully, if you can, know your exponent rules, you can figure out what that one's going to be. A hint, the -2 can go inside the e, and I can show you that in a little bit. I'll just show you that real quick here. If you haven't done this yet, stop this right now, look at it, see if you can figure it out, and come back, because I don't want to give it away. Still have time to stop. And there you are. What did I do? Just use your exponent rules. Nothing based, nothing really that fancy. And now we know that r equals e to the -2. We know our initial term, if we plug in 0, is going to be 1. So therefore, because this is actually 1 over e squared, we know it's less than 1, right? We know it's less than 1. So therefore, we do know that it's going to converge. And therefore, the converging series is going to be 1 over 1 minus 1 over e squared. If you multiply top and bottom by e squared, just to get rid of the complex fraction, you're going to get something that looks a little bit like that. Okay. So those ones are kind of straightforward, well, more straightforward. A couple things that you should, be able to be aware of is stuff like this as well. You have to know that you can separate these as well. And this may be really crystal clear for some of you, but when you see something like this, you got to say to yourself, uh-oh, I got a problem here. Where do I have a problem? Well, I don't have a plane sequence that is going up, right? This sequence is not going up by some common ratio. You got 2 to the n minus 1. So if you can imagine it'd be 2 minus 1, then 4 minus 1, then 8 minus 1. That's going to be what? 1, 4, 7, 15, 31. That's not going up by a common ratio. And because, if you start drawing this out, like if I put in 0, I'm going to get, I need to make this a little more evident. I'm going to plug in 0, okay? If I plug in 0, I get 1 minus 1, so I get 0. Then I'm going to plug in 1, and I'm going to get 1/3. And then I'm going to plug in 2, and I'm going to get 3. I can do this. It's another third, isn't it? I'm going to plug in 3. Plug in 4. And what I want you to see is the fact that it's not going up by a common ratio, right? The bottom every time is going up by 1/3, but the top is not going up. So it's not a common ratio. So you cannot use the sequence here. You cannot say, hey, this is an infinite geometric series, I'm golden. But one thing that you may be able to do, well, actually, maybe you don't know that you can do this, but you can do this, is that you can kind of say, well, I'm going to just do this instead. Now, some of you might be saying, well, why can you do that? Well, my answer is why not? I mean, if you think about it, right, that's what fractions you can do. You can do that. If you have something in the numerator, you're always allowed to split it up into 2 pieces. So you can just say, well, I'm going to take all the left sides and add them all up, and all the right sides and add them all up and subtract them. That's basically what you're doing here. If you start thinking about this, you now have 2 geometric series. This first geometric series has a common ratio of 2/3. This second geometric series has a common ratio of 1/3. And therefore, you can actually figure out the sum. So I'm going to leave that for you to try and do on your own. I'm not going to try and do more than that. I'll let you, and if you have a question, you can always just reach out to me. Okay, so this one's kind of a doozy. Why is it a doozy? Well, clear as day, nobody in their right mind is going to look at this and say, this is clearly a geometric series. You look at this, and it is not your instinct, right? There's nothing at all saying, hey, that's clearly a geometric series. This is where doing this idea of splitting it up and start looking at what's going on may help. So plug in 0. You get cosine of 0 over 5 to the 0. Cosine of 0 is just 1. 5 to the 0 is also 1. Okay, good. Just 1. Now let's plug in -1. What's cosine of negative? Sorry, I meant 1. What's the cosine of just? I wrote that wrong, didn't I? Yeah, I did write that wrong. Let me go back. That made no sense. Now it makes sense. Okay, now it makes sense. So now let's plug in -1. Sorry, let's plug in +1. We plug in +1 for n. We're going to get cosine of pi. What's cosine of pi? That's -1. So we're going to get -1 over 5. Let's plug in 2 now. What's the cosine of 2 pi? That's 1. And 5 squared, I think that's 25. What's the cosine of 3 pi? Oh, -1. Suddenly, this is going to start to materialize as this series is actually a geometric series. You didn't see it at first because you had the cosine away. But if you start thinking about this n pi here, that n pi is just simply every term going from positive to negative, positive to negative. It's just alternating. So the reality is that you could rewrite this as the sum minus, what's the common ratio? -1. Oh, it's going to be +1/5, which looks like it's going to be 1 over 6/5, which is 5/6. So it's a geometric series that was hidden, right? You couldn't see that in the first place. Now we're going to end this video with 3H. We're going to have more time for the next ones. But for 3H, what we have is we have a conversation we had last year about limits. And what we talked about is the fact that what's going on here there's race to infinity conversation that we've had so many times. The race to infinity is this idea that factorials get there really, really fast. Exponentials get there really, really fast. Who's going to win, right? Who's going to win? Well, if we remember polynomials, which are things like, x to the n, don't go quite as fast as any kind of exponential. And they don't go nearly as fast as any factorial. And they don't go as fast as, some x to the x. So therefore, because the numerator is going there faster, the numerator, even though 1,000 is huge, the numerator is going there faster, and therefore, this is going to go to infinity faster than this, so therefore this will diverge. That's why this diverges.